That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on a mote of dust, suspended in a sunbeam. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. There is perhaps no better demonstration of the folly of human conceits than this distant image. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
Hello, and welcome to Astronomy on Tap number 70. My name is Rebecca Larson. I am a PhD student at the University of Texas at Austin, and I will be one of your hosts tonight.
Hi everyone, I am Michaela Bagley. I am a postdoc at the University of Texas at Austin, and I will be your other host tonight.
So let us get started. We're very glad that you're here. We will do everything properly, apparently. Yep, cool. So tonight we have three really exciting talks. We have first up Dakotah Tyler, or Star Kid, is going to be talking about exoplanets during the James Webb Space Telescope era.
Next up, Chima the Exoplanet Explorer, or Chima McGruder, will tell us about finding and characterizing habitable exoplanets.
And last, we'll have KeShawn Ivory, or Halo Handler, telling us about improving the methods of galactic archaeology. So I'm really excited for our show tonight. A few intro things to get us started. First off, of course, science is better with beer, or whatever it is that you are drinking at home. We're sad that we cannot be in person tonight, but we are happy that people from all over the globe can watch this show. So go ahead in the comments, let us know when you're chiming in from. If you were here, we would be at the North Door, and we want to give a special shout out to them for being an amazing host to our show for the past several years, and also to the Austin Astronomical Society for being our sponsors, and for Odell Brewing Company, which is what I will be drinking tonight.
As Rebecca mentioned, we really want to give a special shout out to the North Door, our venue. In the past, we've been collecting some donations to help support them, but we've now removed ourselves from that process. So please consider supporting the North Door through these difficult times. They've lost a lot of revenue, of course, being closed for so long, especially losing the South by, the huge crowds that they would have gotten during that time. So we've put their Venmo up on this slide. And at the same time, while you're drinking your beer, what goes better with beer than tacos? Don't forget that Pueblo Viejo is still open for takeaway, so you can get your tacos there like I did. I'm ready for the show tonight. I'm so excited.
I'm so glad.
There isn't a good way to show that off without it falling in my lap. But right, make sure to support both the North Door and Pueblo Viejo during this time.
So connect with us when we're not live. You can watch any of our previous shows on our YouTube channel, which is hopefully where you are right now. So go ahead and subscribe to that if you're interested in getting notified when we do go live, but also check out our back catalog of talks from the last 70 shows. If you have Facebook, you can find us at Astronomy on Tap ATX. If you have Instagram or Twitter, we're at AoTATX. You can also send us an email if you have any kind of questions. And we have a really cool announcement. We have a new website. So check out AoTATX.org. And if you want to learn more about Astronomy on Tap as a worldwide organization, check out astronomyontap.org. All of these links are in the description of the YouTube channel, and we have special moderators that are sharing those in the chat for you.
During the show, feel free to ask questions over Twitter or in the YouTube comments. If you're using Twitter, please use the hashtag AoTATX70 to help us find your questions. And feel free to ask questions at any time during the speakers' talks. Like Rebecca mentioned, we've got awesome people who are checking out the YouTube comments and Twitter, and they will collect those questions for us so that we can ask them. So don't wait until the end of the talk to ask your questions, just shout them out there and we'll get them. We'll do our very best to answer as many as we can, and if we can't get through all the questions, we might bring our speakers back up after to have a little bit of a panel discussion. So don't hold back.
We are doing trivia tonight. Again, we are not in person, as you are clearly aware, so we do not have our trivia forms for you. You don't have to write legibly, just type or click buttons. You can find the trivia at this link that we are showing here. It is also in the chat. It is also in the YouTube descriptions. All of the questions that will be answered by our speakers during their talk. So if you would like to hold off answering all of those questions until you are absolutely sure you've been listening carefully enough, we do have trivia prizes for you. We are definitely going to send those soon. We also have all of our answers that we will post later this week. So if you are not watching this show live, you still get an opportunity to play trivia with us. If you are interested in being informed if we're going live or any of the things that we're going, you also have the opportunity to sign up for our mailing list and be part of our subscribers, and all of that will be in the trivia form as well. Michaela, I think you should be the one to talk about this last point.
Yes. So as Rebecca mentioned, we do have our new website, AoTATX.org. And if you go to /trivia, we have finally posted all of our answers to previous trivia questions. So we started off when we were virtual by trying to put our answers on Instagram. Turns out we're not super good at staying on top of that. But if you are curious about the trivia from any previous show, they're all there. All of the virtual shows, at least, are available on our website. And the answers to this week's show will be there by Friday. Don't forget to play our trivia. Sorry, Rebecca. Don't forget that you do not have to get all the answers correct to get a prize. We choose some random winners. So play and don't worry about getting all the answers right.
Exactly. We are non-discriminatory. On that note, please be kind to each other. Be respectful with your comments, with your questions. We are virtual. This is still a no harassment zone. We do have moderators moderating the chat. Be good humans. This is a safe place for everyone, and we really want to make sure that we're bringing you astronomy and none of the other crap. So, on that note,
let's get started.
All right, so first up, we have Dakotah Tyler. Dakotah, would you like to join us? Dakotah is coming to us from soon-to-be UCLA. Before he completed his career as a football player at the University of Kentucky, now he is pursuing a passion for astronomy that culminated in him completing a BS in physics and astrophysics at the University of Cincinnati, with research experience in protostellar disks as well as exoplanet atmospheres. He is currently working with NASA on the JWST program. One moment. Until he moves to California to study exoplanets in graduate school at UCLA this fall. I have a feeling that I'm going to have to get another drink before your talk is over, sir. So go ahead and take it away.
All right, everybody hear me?
Yes, sir.
So as Rebecca said, I'm going to be talking about exoplanets, particularly under the James Webb Space Telescope era. So James Webb is a telescope that is being launched very soon, and it is going to revolutionize a lot of things about astronomy, particularly exoplanets. To start this out, though, I want to give everybody a nice reference point. Most people are familiar with the solar system objects, so I want to use them to kind of group up the different types of exoplanets that we can search for. So there's rocky planets, which are also called terrestrial or Earth-like, but it's important to kind of point out that although we call them Earth-like, they're really not Earth-like. They're just kind of Earth-sized. They could be Venus-like, they could be Mars-like or Mercury-like, but we just call them Earth-like because we're humans, and I guess that's how we roll. So then we have the gas giants. This is Jupiters and Saturns. These are enormous planets that are mostly hydrogen and helium. And we have our ice giants. So these are gas giants as well, but they tend to be colder. They're made of heavier elements than just hydrogen and helium, usually methane, CO2, things like that. And you already know the drill. If you don't, I'm sorry that you got to find out this way, but Pluto, we don't really rock with like that anymore. So now that we have the basic demographics, I'm going to talk about ways that we detect exoplanets that are applicable to James Webb. So one way is the transit method. So during the transit, we basically stare at a star. And in this video here to the left, you can see the planet clearly moving around, but when we stare at a star, all we really see is a dot of light. But what we notice is that there's these periodic dips in the light that we receive, and then there's a smaller dip as the planet goes behind the star. So by judging these periodic dips, we can infer a planet's presence. And the cool thing about this method is when the planet passes in front of the star, although it blocks out a lot of the light, some of the light goes through the atmosphere. So we can actually get a spectra of what that atmosphere has as the photons interact with it. This has, to this point, it's been limited by a few factors. Usually we can only get decent atmospheric analysis from the gas giants, and we aren't really able to say much about exoplanets that are more Earth-sized or Earth-like. So another way of detecting exoplanets is by doing it directly, like actually taking a photograph of the planet, which is what you can see here in this high contrast direct imaging method. So what we do is we take a coronagraph, which is this black circle that we basically put on the star. And when we block out that light, you can see the other planets orbiting around. So you can see 4 here. There's 3 to the right, and there's 1 over to the left. So this was taken by a ground-based telescope, and it's really hard to do. It's very difficult. The planets have to be very, very massive, and they have to be very far away from the star. This is only possible in young star systems as well, because what we're looking at is infrared light, which is heat. So these planets, they still are giving off heat, and that's because they were recently made. And when I say recently, it could be hundreds of millions of years, but on a cosmic timescale, it's not really that far. So these are young stars. But one of the major benefits to this method is not only that we can study stars or study planets that are far away from the stars, but we can do a direct spectroscopy versus the transit spectroscopy, where we have to try to disentangle light from the star and the planet. So this is where James Webb comes in. Most of what James Webb initially intended to do was build off of observations made from the Hubble telescope. And over here on the left, you see this graph. I have highlighted this HST, Chandra Deep Field, and JWST. And basically what this is showing is that JWST, this new telescope, is going to be able to see further than the previous telescopes could. And that's because it's more sensitive. And how does this happen? It's huge. You can see right here, Hubble is about the size of a human, and JWST is like the size of a tennis court. And it's shaped like a honeycomb, which is kind of cool because it's so sensitive that you could see a bumblebee on the moon if you wanted to. So now I want to talk about what that sensitivity means as far as the transit spectroscopy. So we already know a ton of exoplanets that are Earth-like. They're small. Again, they're Earth-sized. That's about as much as we know about them. But we haven't really been able to detect or characterize their atmospheres. So that's obviously something that we want to do. Personally, as an exoplanet researcher, and honestly, I feel like everybody on Earth probably wants to know if there's life somewhere else. And it's hard to do. It's hard to detect. This stuff is so far away. But one way that we can start to begin to step into that direction is analyzing the atmospheres of these Earth-like planets. So what JWST is going to be able to do is, at the very least, get a basic composition of some of the atmospheres of these planets. So maybe they are dominated by CO2 like Venus, or maybe they'll be dominated like by nitrogen like Earth, or something else altogether, H2O, whatever it may be. We're also going to be able to characterize the gas giants, the Jupiter-sized planets that are very close to the star, which is unusual if we're thinking about our solar system. But it's not all that unusual to have gas giants that are in the inner star systems that we look for. Another thing we're going to be able to do is check out the abundances in the atmospheres, which is important because, you know, the planets and the stars, they're made in the same disk. They're made in the same bunch of dust and material and molecules, and different elements tend to be at different points in the disk. So we think that planets maybe form here or there and then migrate over time. And that's something that we're going to be able to say more about once we understand these abundances a little better. Another thing I want to point out here is this TRAPPIST system that I have posted is very, very small compared to Earth system. So you can see that it's actually zoomed in. All of these planets, all 7 of these Earth-sized planets orbit inside of Mercury, which is already on a short orbit of only 88 days. So there's a few of these planets that are in the habitable zone, which can be misleading. We call it the habitable zone because we know that water can exist in this region, but that doesn't necessarily mean that the planets are going to be habitable. Habitability relies on different factors. One of them is atmospheric composition. Another one is plate tectonics or other planetary phenomena that goes on. So just because something's in the habitable zone doesn't really mean that only a planet in that zone could be habitable. Sometimes it could be shorter, longer. It kind of depends individually on the planet. So when talking about direct imaging, James Webb is like really gonna shine. Here, this is applied, and I know there's a ton going on, but just bear with me. You can tell that there's clearly, these are all the exoplanet observations that we have. There's, you know, thousands of them. I pulled this from Caltech's Exoplanet Archive. And I posted Jupiter, Saturn, Uranus, and Earth so that you could kind of see where the planets that we know about in our system fit into what we found so far. You'll find that Earth is over here by itself. So, you know, Earth-like planets, I mean, we've not really found an Earth-like planet, both in size and distance. Same with Uranus. It's over here by the timing variations in the legend. And you really can't say that we've found any planets like that. And the reason is either that we're totally unique in our solar system and there's nothing else like us, or we just haven't quite been sensitive enough to make these detections to find these planets. James Webb will be sensitive enough to fill out this lower right-hand portion of this graph. Everything is kind of skewed up and to the left because that's close, it's proximity to the host star and size. You see a lot of these planets are larger than Jupiter, which is kind of difficult to wrap your head around because it's a huge planet. So I want to talk a little bit about exactly how James Webb is going to be able to do this, but I don't want to go too much into like the technical aspect. I want to highlight this piece right here. So the image that I showed earlier was taken with Keck. It's the ground-based telescope, and you know we use the coronagraph, and you can see planets that were orbiting. And this is its sensitivity level. So this is a contrast graph. You can see that it's about 10,000 or maybe 100,000 times fainter the planets were than the star. And if you look at the pink and red lines at the bottom of the graph, these are different coronagraphs on James Webb, and they're much more sensitive, up to 100 million times fainter than the star. So if you think about what that means, which, you know, what's 1 million times less or 100 million times less? So I'm 1.8 meters, and nobody knows what that is. I'm 5'11", right? I got a little shorter ever since I started shaving my head, but I don't know how that happened. But so at 5'11", 1 million times shorter than me would be something that's like the thickness of a human hair. 100 million times shorter than me would be something that's like on the scale of a virus, like something in the nanometers. So just, which that also may not mean anything, because like who knows how small like a virus is. It's hard to think about that as well. So I also weigh 215 pounds, right? So something that weighs 100 million times more than I do would be, I don't know, like the Great Wall of China or something like that. Like the whole thing, all 13,000 miles of it. So these scales are ridiculous. Basically, JWST is super, super sensitive, and we'll be able to see things like Uranus-sized planets at orbits that are 5 AU. So maybe from Jupiter out to where those planets actually are in our system. So to wrap everything up, I just want to talk about make sure everybody comes away from this talk understanding the 3 main areas that James Webb is going to affect exoplanet research, how it's going to revolutionize what we understand about them. And that's with the rocky and terrestrial planets, and even the super Earths, the slightly larger than the terrestrial planets that we have. We'll be able to detect and characterize these atmospheres for the first time ever. We've not really been able to do that, but we will be able to do that for sure. We'll be able to compare the abundances with the star to see how the evolution of the system is working. And we can even make comparisons to our own solar system and see where we fit in on a universal scale, or at least a galactic scale. And this is absolutely the next big step in searching for life biosignatures. We're not going to find life conclusively with James Webb, but this is the next step in that direction. When thinking about these gas giants, the Jupiter-sized, Jupiter-plus-sized planets, we're going to be able to characterize these atmospheres even better. We can a little bit to this point, but we'll be able to do it even better, and we'll understand hopefully a little bit more about the evolution of these planets and whether or not they all migrate in, or some of them stop migrating in. But we'll get a better feel for the star-planet interactions. And lastly, the ice giants. So you saw from the plot, we really have huge knowledge gaps about these ice giants, the Uranus and Neptune-sized planets. And we'll be able to hopefully fill some of that in with the sensitivity that James Webb has. And doing direct spectroscopy on these planets is going to give us a better spectral classification and allow us to understand more about them, of course, than we do now. And it's going to answer a lot of questions about why these planets at this distance seem to be less prevalent, or they seem to be a bit more rare. Hopefully we can understand if they tend to get ejected out of the system, or if they all migrate in, or whatever it is. James Webb really promises to answer a lot of these questions. So thank you all for giving me that chance to give the talk, and I'll pass my acknowledgements. Here we go. Yeah, so acknowledge NASA for paying me to do this, JWST program, of course, and then my advisor at NASA, Eric Smith.
Awesome. Thank you, Dakotah. Awesome talk. I just want to acknowledge that for those who don't know, Rebecca has a thing where she has to drink every time somebody says JWST. So, you know, we're just going to say it a couple more times here in the
You're
question.
such a jerk.
So Dakotah, come on back. We have some questions for you. Thank you again for that great talk. Really exciting stuff. As not an exoplanet person, you get me excited about what Webb will do for this field. That's awesome. So let's see, we've got a question from Richard, who's asking, I think referring to your contrast curve diagram that you showed. Mm-hmm. What did the times mean, the 100 million years? What did that mean under the masses of the planets? I guess what role or what does
under the masses? Oh, okay. So these are ages. All right. So you're talking about so like a 10 mass Jupiter, and then there are the times underneath. So these are the ages, right? As time goes on, remember I said that the direct imaging was in the infrared. The reason we can see these planets is because they're young. which means that they've still retained some of the heat from formation, but as time goes on, they do cool off over time. So it becomes harder to detect them as time goes. So you'll notice that the times, the higher times are lower.
Like lower contrast.
Yeah, like a lower contrast in comparison with the star.
Cool. How long does it take a planet to cool off? I don't know, maybe a planet like Jupiter.
A Jupiter-sized planet to cool off?
You can make it up. I won't know.
I would say hundreds to a billion years, maybe.
Cool. A long time in astronomy. Awesome. Okay, so we've got a question from Jeff, who says, when you get time on the JWST, where's the first place you're going to point it and why?
So first I'm going to look at the moon and try to find that bumblebee. But after that, I would definitely be interested to see what's going on in the TRAPPIST system that I showed, as well as there's numerous systems found by Kepler that have kind of similar numbers or demographics of planets that we have in our own solar system. I mean, I would just be interested in looking at every possible Earth-sized planet and see what we can learn from it. So yeah, I mean, if they let me have control of the JWST time, the only thing we'd ever learn about was Earth-sized planets.
Nice. That's awesome. Okay, Miriam is asking, can you tell us a bit more about the work you did on JWST?
Right. So what I'm doing right now for HQ, which for those of you who don't know, HQ is like more of a, I guess, the administrative side of NASA, is gathering and trying to compile a forefront of where we are right now in the field of exoplanets, specifically with regards to JWST. So I didn't work on JWST. I'm just working on kind of, like I said, compiling everything that we expect to happen between the early release science and the guaranteed observations, and where we are right now, like kind of where we can't get past just due to the fact that we are, kind of prisoners to whatever technology that we have at a specific time. So the instruments on James Webb are going to take us to the next level. And I'm trying to encapsulate exactly what ways that it will be able to do that. That we would be able to look back on in it, say a year or two, and be like, oh yes, like these are very clear, specific ways that James Webb has advanced the field specifically of exoplanets.
That's awesome. That's really, really exciting. I'm going to say something controversial in that, working on the instruments is important and exciting, but it sounds like you're playing a huge role in like determining the direction of your field. That's really cool.
Yeah. And starting grad school, it's been really helpful to kind of get a really good understanding of where exactly we are in the field. I feel like I kind of got a jump start in, everything that's going on.
Nice. Awesome. Well, if you're able to stick around, we'll have some more questions for you at the end after all the talks. Thank you again for your great talk, and we'll see you a little later, hopefully.
All right. Thanks. Thanks everybody for checking it out.
So next up, we have Chima McGruder. Chima, can you join us with your video, please? Excellent. Hello.
Hey.
Chima is a rising fourth-year graduate student at the Harvard Center for Astrophysics, where he studies exoplanet atmospheres with his advisor. He's currently focusing on studying the planet and star via transmission spectroscopy with ground-based telescopes, with a particular focus on the methods and techniques and strategies that are necessary to disentangle the signals from the stars and the planets. So with that, take it away.
Okay, let me go ahead and share my screen. Beautiful. Can you see all this?
Looks good.
All right. Okay. So as was introduced, Chima McGruder, and I work at the Center for Astrophysics, the Harvard Center for Astrophysics, as a fourth-year graduate student with my advisor, Mercedes Lopez Morales. And I'm going to talk to you about how about finding and characterizing planets in the habitable zone. So this has a lot of, this will help answer a lot of questions that we've had for centuries, in particular the philosophical question of are we alone and what that means, the biological question of exactly what life needs to form, and the future exploration questions of is it worth exploring outside the solar system, with hopes of finding little green pups like these. Okay, so particularly I'm going to be talking about what makes a planet habitable, so the specific building blocks for, we think, for life to exist. What we need to do to find the right planets, so filters that suggest that this planet is habitable, and signs of habitability when you specifically probe particular planets, in particular its atmosphere. And then once you do that, how exactly are we going to probe the atmosphere? So what makes a planet habitable? For full disclosure, there's a lot of work done on why or how organisms form on different types of, how organisms could form on bodies with very different physical situations as the Earth and very different chemicals available for biochemistry. However, I'm going to be talking about habitability in the context of our one data point, which is the Earth. Okay, so there's a few building blocks that I've listed here on habitability and what organisms need to form. This is arguably in the order of importance, the first being water. Water is an extremely versatile molecule. It can be used for dissolving nutrients and minerals. It can be used to flush out toxins. It can be used as a transportation mechanism within the body or the organism, and it can be used as a as a temperature regulator. And it has a bunch of other versatile uses that organisms utilize. In fact, water is in every single organism in some form or fashion on Earth. In addition to water, you need energy. This energy will drive the biochemical reactions that organisms undergo. And in particular for Earth, the majority of the energy is driven in the form of light, UV radiation, and photosynthesis. However, there's over 300 organisms found in hydrothermal vents deep in the ocean where UV light cannot reach. So they have utilized the geothermal energy to supply their biochemical reactions. In addition, there's specific abundances of elements that we need. This is known as CNOPS, and it's used by all organisms in different ways. In particular, for example, DNA uses CNOP, which is carbon up to phosphorus, and 98% of the makeup of organisms is of CNOPS. So now that we have the what we call the ingredients for making life, we can use this as filters to figure out which planets are likely to have life and which are more likely to have life than others. Initial filter, which Dakotah so graciously introduced for me, is the habitable zone. So the habitable zone is just the region where liquid water is believed to be present. So the planet needs to be far enough away that all the water is not vaporized, but also close enough that all of the water is not frozen. And so because the planet is not too hot and not too cold, it's also referred to as the Goldilocks zone. For a particular planet star system, there's a lot of chemistry and physics that needs to be considered. So the particular composition of the planet's atmosphere, additional heating sources for the planet, the radius of the star, chemical composition of the star, the stellar type. However, when you make plots such as these, you're considering relatively few parameters such as the mass and the distance of the star. So now that we have this initial filter of can this planet retain liquid water, how do we find such planets? So over here, I've listed 4 of the techniques in finding planets, 4 of the main techniques in finding planets. And over plotted that is this blue region, which is the habitable zone. So as you can see here, the red transits and the orange radial velocity are the 2 main methods in finding planets in the habitable zone. Radial velocity is where you measure the periodic wobble of the star due to the planet's gravitational pull. Just as the star is gravitationally pulling on the planet gravitationally pulls on the star. And if you have high enough precision velocity, you can measure this change of motion over time. Transits was Dakotah explained very well. It's just when the planet passes in front of the star. This graph did a very good job of showing that. And because the planet is blocking a significant fraction of the light from the star, the system dims. And as you can see here in the blue, the orange, which is radial velocity, is currently the primary way of finding planets within the habitable zone. However, the red, which is the transit, which I will talk further, is very important for observing exoplanet atmospheres in depth. So other filters we can use are if the planet is terrestrial-like. So terrestrial-like means that the planet has similar mass and radius towards the Earth. So an example of this is K1218b, which earlier this year was found to have water in its atmosphere and is within the habitable zone. However, the mass of this planet is nearly 9 times that of Earth and nearly 3 times the radius of Earth. So this planet is most likely not going to harbor life because it's a very different physical situation of what we believe life forms in. Okay, so now we have these initial filters of mass, radius, and able to retain liquid water. We want to probe further these specific planets that fit the bill. And to do that, we look for biosignatures. Biosignatures are observables that we see in a planet or a system that is unlikely to produce naturally. So it's not produced abiotically. And examples of these are gases such as oxygen and methane, or light in the spectrum of the planets, such as reflected light from an excessive amount of reflected light because of vegetation. So this is known as the red edge, where a large amount of near infrared and red light is reflected off of the planet. But it's important to be cognizant of false positives. So false positives is when you observe a possible biosignature, but is actually produced abiotically. In fact, the planet doesn't harbor life. So for example, if you have oxygen, there's multiple ways in producing oxygen and methane in abundance. However, if you see oxygen and methane together, because oxygen and methane don't agree chemically, and you observe an overabundance of them, it means that something is continuously pumping it, implying that this could be caused from life. And in addition, if you see a red or the red edge from vegetation, it'd be very hard to refute the idea that this is caused by life. Okay, so now that we know exactly what we're looking for, how do we do this? So I've shown here the 4 main ways of probing exoplanet atmospheres. Transmission spectroscopy, as Dakotah graciously explained, is when you look at the star in different wavelengths, and because each molecule in the atmosphere of the planet absorbs different wavelengths of light, the depth of the planet will vary based on the abundance of that specific molecule. So you can see here, there's 3 wavelength channels that we're observing in, and they each represent a different molecule. And the green here is not very abundant. So the depth, so the size of the planet, the depth of the transit is smaller. And the orange is overabundant and has a much larger depth. Direct imaging is when you just look directly at the star, which Dakotah addresses has a huge caveat of the fact that this, you directly image the planet. And then the huge caveat is the fact that the star is much more brighter, orders of magnitude brighter than the planets. So you have to be creative in blocking out the light from the host star so the spectral features of the planet is not washed out. Emission spectroscopy is similar to transmission spectroscopy, except the planet is going behind the star. And when the planet goes behind the star, the system dims slightly because the light from the planet is being blocked from the star. And then from that, you can deduce what light is coming from the planet. High resolution spectroscopy does a similar idea as radial velocity in the sense that the motion of the bodies causes shift in spectrum. So the planet and the star are going to be moving at different velocities towards this velocity to also change in wavelength. This is Doppler shift. And so supposing the planet away from you and then moving towards you at a certain velocity, if you have high enough resolution spectrum, you can disentangle the star. They're slightly shifted. So as I alluded to previously, transmission spectroscopy is the dominant way that we currently observe exoplanet atmospheres. However, as Dakotah mentioned, transmission spectroscopy even still is unable to probe finally the atmospheres of terrestrial-sized planets within the habitable zone. So fear not, we are working diligently to improve that. Our limitations are techniques, instruments, and telescopes. And over here, I have a list of new telescopes that are either under in concept or in development near launch or under construction. And for example, space-based telescopes such as LUVAR and HabEx will be very good at direct imaging exoplanets. And the next generation of ground-based telescopes will be very good at high-resolution spectroscopy of exoplanets. So even though we have yet to find biosignatures of exoplanets, we are diligently working to find little green pups. Thank you.
Thank you, Chima. I love that puppy so much. Whose puppy is that? Is that yours?
No, so last week I went on a cabin with some friends, and one of them had a pup, and she really wanted that pup to be famous, and it's on its way to be a famous alien.
What's his name?
Basil.
Basil is so cute. I hope he is
Yes.
famous. He's famous at Astronomy on Tap now, so mission accomplished. Thank you so much. That was a great talk. So we do have a few questions for you. So first we have a question from Prince, who wants to know, what is the best technique to find the habitable zone?
So, okay, so finding the habitable zone depends on the star system, and generally it's just related to distance relative to the stellar flux coming from the star. So the stellar flux coming from the star varies, but if you have a given mass, a given stellar type, and a given luminosity of the star, then you can determine how much heat is reaching the planet. And then you also have some more variables specifically for a given planet, which depends on additional heating sources like tidal heating, which is tension from gravitational pull, and how well the atmosphere retains its heat. But overall, for generally speaking, it's just the brightness of the star and the distance the planet is from that star.
So there's a lot of comments and questions we also have asking you, we've looked at the habitable zone as a place where we can have liquid water, where we think carbon-based life forms could live. What about potentially other element-based life forms? Are we just caring about the carbon-based possibility?
So you can be carbon-based, or sorry, you can be not carbon-based, but also still need water. So there's a lot of research underway. Sarah Seeger's a prime example at MIT, doing research on what other molecules organisms can use to power itself or to structure itself. But it's very complicated because there's a slew of compounds that could potentially be used for life. And we don't have any direction other than Earth as to where to go. So that's why we generally think of water and carbon-based, because that's favorable on Earth and is also chemically favorable.
So it's one of those kind of like, we have a sample size of 1. How do we determine if there's any other possibilities, huh?
Exactly. So the sample size is of Earth, and then we are exploring a huge realm of other options, but the realm is just so massive that it's very difficult to actually say anything, whether it is possible or not, until we have something to prove it.
So would we be able to determine if there is in a planet's atmosphere any other signatures that would be indicative of life of a different kind?
So yes, you can get biosignatures that would not be of life similar to Earth, but again, it's going to be much harder to false positive. So you can get bios of is present in the atmosphere, is chemically unfavorable, so it like requires a lot of the planet to form, which would suggest that life. However, there are some edge cases where it could be formed abiotically. It would be extremely hard to confidently say that it is life.
Well, that's really enlightening. And I hope that with our new generations of telescopes that we're able to shed even more light, pun intended, on this problem. So thank you again, Chima. You did a great job. We are going to move on to our next segment. So if we can have our dynamic duo join us here. We have the news coming up.
Hello.
Astronomy in the news is next. We have Jackie and Danny. So go ahead, take it away.
Hello.
Hello.
Welcome to the news, everyone. Let's see. I remember how to share screen this time, so look at me.
We're all down to about 2 brain cells now.
Oh, 2 is being very generous. Whoop. There we go. Okay. Welcome to Astronomy in the News for July of 2020. We have some exciting news stories coming up to share with you. And so this first one, right, I mean, I'm an astronomer, but I often joke that I actually can't really tell you anything about what's up in the sky at any given point, right? Someone comes up to me and is like, oh, what's that bright thing over there? And I say Jupiter, Saturn. I really have no idea. I'm very sorry. But in a bit of a change of pace, for this news story, I'll be telling you about a relatively new comet that you can actually go out and see in the night sky right now. And I will actually tell you where it is in the night sky. So that's 1 point for me in a lifetime of knowing where something in the sky is. So Comet C 2020 F3 Neowise, love an astronomy name, often just called now Comet Neowise for short, was discovered only this past spring at the end of March by maybe aptly, the NEOWISE mission. The NEOWISE mission is an extended mission with the WISE infrared telescope. After it lost some of its coolant, it was in a bit of a warmer mode, and so it couldn't do as precise measurements as it had in the past, and so they changed the mission to look for and track near-Earth objects, which is NEOWISE, New WISE, Near-Earth Object WISE. Sometimes astronomy acronyms can actually make a lot of sense, but there's maybe only two of them other than this one. So what is Comet NEOWISE, right? A comet is just a ball of ice and dust that is flying through our solar system, originating from the outer solar system typically. Comet NEOWISE is about 3 miles wide, which is typical of many short period comets, although that's still a few times smaller than, you know, the well-known Halley's Comet, or much smaller than Comet Hale-Bopp, which was kind of the great comet towards the end of the 20th century. It's on an extremely eccentric orbit, which basically means it gets really close to the sun, but it also gets really, really far from the sun. And its orbit is actually so eccentric that it's barely bound to the solar system. So if something were to change to its orbit, it's possible that it could yeet off out of our solar system. There, I'm sorry if I preempted your yeet, Jackie.
I have my drink of water for a family-friendly drinking game.
There we go. Every yeet you can take a sip. Although I think that's my only yeet for the day. And so this comet is on thousands and thousands of year orbit, which sounds like a really long time. I mean, I guess it's really not that much longer than we've been dealing with lockdown and the pandemic, but it's actually somewhat in the middle of a typical comet period, some of which can actually extend to millions of years that they take to go around the sun. So why care about comets other than that they can look pretty cool in the sky? Well, they're really important for our understanding of the origin of our solar system, the origin of the planets, and really the origin of life here on Earth. They're really solar system fossils, right? These balls of ice are left over from the formation of our solar system, and they're mostly kept pristine, which means that their composition is indicative of the conditions in our early solar system, right? And particularly they're important for our understanding of water content and organics in the solar system, right? We're not entirely sure. Right, I mean, there's different ways that Earth could have gotten its water content, one of which could have been from comets in the outer solar system. So understanding the comet population of our solar system is a key constraint on our models of how the solar system formed and its early evolution. And so while this comet is still in the sky, there'll be more and more observations done by astronomers. One recently, they studied the sodium content in the tail of the comet, which, I mean, okay, sodium's in the comet, that's great, but those can typically be only observed in very bright comets, a comet like this. And so when a comet is bright, like Comet NEOWISE is, it really provides a very unique object of study for cometary studies. And so, of course, the coolest part is that you can go outside and see, okay, well, I don't think, not right now, but you can go outside and see the comet for yourself with your own eyes, right? So Comet NEOWISE just recently passed by the sun, its closest approach to the sun, and it will actually be closest to the Earth in just 2 days. So while it already reached its peak brightness, about roughly the same brightness as Saturn in the night sky, and it's unfortunately dimming now that it's moving away from the sun, it's still bright enough to see with just your eyes, although a pair of binoculars would definitely help if there's any light pollution or if you want to make out its tail in the night sky. And so if you want to go out and pick out this comet, if you go out just after sunset, I want to say within like the hour after sunset or so, if you look to the northwest, you should be able to see Comet NEOWISE just to the left of kind of the bottom of the Big Dipper. Now, it might not look as grand as it looks in this picture here on the left, but you'll still be able to see a comet that won't be back in Earth's night sky for about 10,000 years. So I don't know, I guess that's kind of a big deal.
I don't know if there are any Tim and Eric fans out there, but it always makes me laugh how many like accidental references there seem to be to their fake space documentary. And my favorite quote is, "There are hundreds of stars in the sky, and all you have to do is look with your eyes." And that seems to be every amateur astronomy advice. So unfortunately, I was beaten to the Yeaton, but it would not be news with me if I didn't make my same talking heads joke that I make every single month. So here we go. After months of isolation, we were all at the quarantine stage of finding ourselves at the wheel of a large optical telescope. And we're asking ourselves, well, how did we get here? If you're instead at the brain dead stage of quarantine like me, you can at least trust the cosmologist to ask the big questions. So this week, the Sloan Digital Sky Survey absolutely dominated the archive, which is where most astronomers get their daily astronomy news, that and Twitter, with an impressive 23 papers submitted to the monthly notices of the Royal Astronomical Society. If you are a TikToker, you might be familiar with e-girls and e-boys, but move out of the way because we have reached the final e-boss, the Extended Baryonic Oscillation Spectroscopic Survey. The Sloan Digital Sky Survey has been operating for nearly 20 years at the Apache Point Observatory in New Mexico, which is a vast wasteland that I hate. But it is a spectral imaging and spectroscopic redshift survey aimed at determining the redshifts and precise spatial locations of millions of galaxies in the universe. And on July 20th, they released their comprehensive analysis of the largest 3D map of the universe we have ever created. Will Percival, the survey scientist, explained that eBOS uses the baryonic acoustic oscillation technique for distinguishing galaxies' locations and measuring the expansion rate of the universe. I'm not going to explain what that means because I don't know. But trust me that it is a very valid use of science and gets us the most precise locations of galaxies possible, and I will explain why in a second. So in finance, they like to say time is money, but in astronomy, we say time is distance. And because we astronomers absolutely hate characterizing distance in terms of sensible units, here's an absolutely useless radius, which is that the image you're looking at is a radius of 11 billion years of cosmic history, which is 80% of the age of the universe. The fourth edition of SDSS took observations between 2014 and 2020, and the new map contains over 4 million objects, including a range of different things, which you are seeing in the different colors on the map. And it includes nearby galaxies, distant star-forming galaxies, young blue galaxies, high redshift quasars, and the very highest redshift objects are Lyman alpha emitters, which are the young hydrogen-rich galaxies thought to be foundational in early star formation. And this really pushes us to the edge right after the Big Bang, or before in distance units, because time and space are both fake. But the new map allows us to see the filaments of the cosmic web and map out the large-scale structure of the universe, which is something that any of us might do on a lazy Sunday afternoon, but it is in fact quite the task. What makes redshift surveys so challenging is the difference between cosmic redshift, which is the movement of galaxies and objects away from us in general due to the expansion of the universe, but that also fights with their local or peculiar movement, which is due to nearby gravitational pulls. So overall, the universe is expanding and generally everything is getting further away from you, but in tiny pockets, things like a nearby galaxy or on the smaller scales, nearby stars and planets are also exerting gravitational pulls, which makes things look a little bit closer. And so while a lot of things are sensitive enough to get a general cosmic redshift, actually getting peculiar velocities is pretty difficult. But this baryonic acoustic oscillation thingy is really useful for that. And that's the end of me explaining that. But the fun doesn't stop there. There are other methods of measuring the expansion of the universe, if that keeps you up at night. The eBOS map is also hot on the heels of another exciting result coming from the Atacama Cosmology Telescope in Chile, which uses my much preferred wavelength of millimeter waves in order to measure the thermal thumbprint of the Big Bang, also known as the cosmic microwave background. They report a new, more precise age of the universe of 13.8 billion years, give or take a cute little margin of 20 million years, or a dinosaur era or two. And you can follow the bit.ly link that I have placed in a helpful box to see a 2D and 3D zoom in of this breathtaking eBOS map, and they will explain more about what I was talking about. And if you're bored, you can read all 23 papers on the archive. So that's that on that.
Ooh, God, imagine publishing 23 papers in one day.
No. Can't relate to even publishing one, so.
Oh boy. So unfortunately, this month, there were no news stories that I could report involving my favorite icy moons of the outer solar system, but that does not hinder me being able to gladly bring news of missions of exploration beyond our own Earth. And it seems like the fascination with the red planet knows no borders, as there are a whole 3 missions to Mars around the world that have or will be launched by the end of this month. So first up is the Emirates Mars mission, or the HOPE orbiter, which is a satellite mission to Mars launched by the United Arab Emirates, its first ever interplanetary mission, which is pretty exciting. The mission launched just a few days ago on July 19th, and it will reach Mars in February of next year. And so this satellite hosts 3 instruments that will be used to probe and better understand Mars's tenuous, thin atmosphere. And what's really cool about this satellite is it's going to enter into this unique orbit where it will orbit Mars right above its equator. And by doing this, it will actually be able to study the Martian atmosphere consistently over the course of a full day and a full Martian year. And so you can really gather state-of-the-art data on the weather, seasonal changes, and climate of the planet, which we still don't have, fully realized models of. And of course, this data will not only help us understand the Martian atmosphere, but improve our models of planetary atmospheres and evolution in general. So next up, the second mission is China's Tianwen-1 mission, which will be launched sometime this week. And it's interesting in that it contains both an orbiter and a lander and a rover, all in one. And it's also set to reach Mars next February. So hopefully they have, connected and they're not going to crash together or something when they get to Mars. That would be really sad. But so this is also China's first mission to another planet. And so what is really interesting here, like I said, it's both an orbiter and a lander. And so when it gets to Mars, it will orbit for 2 to 3 months, observing and mapping the surface of the planet before actually landing the rover on the surface. And once
yeeting itself?
Yeeting itself onto the surface. There we go. Okay. I already gave you a yeet, okay?
You're right.
More than usual.
The people need more.
So the rover's main science objectives are mostly going to focus on the composition of the Martian soil and any water presence in the Martian soil, which is kind of, the hot topic these days. And it will also be searching for potential signatures of life, past or present, on Mars. And so lastly of these 3, we have NASA's new flagship mission to Mars, the Perseverance rover, formerly known as the Mars 2020 rover, which always seemed like a decade away to me, and now it's here. It's, as Jackie would say, time is fake. So this rover will reach Mars, I believe, also in February or March of next year. So again, a very hopping time for Mars, getting a lot of new friends. And so this rover hosts a very large payload of nearly 10 instruments that are designed to do everything from image the Martian surface, monitor the weather at the surface, and have multiple instruments that can perform different detailed analyses of the surface composition on Mars. And so hopefully it will find more information about water under the Martian surface, and even hopefully detect organics or signatures of previously present life on Mars. And actually, I did not know this next part, but I think perhaps the coolest thing to me is that Perseverance will arrive on Mars with a little buddy, Ingenuity, a helicopter that will be there to kind of scout ahead of the rover and help plan the best route for the rover to take. So I'm sure there'll be really cute art of Perseverance with a little helicopter buddy flying around it. So I can't wait for that in a year. And so while you all know my love really lies in the outer solar system, it really is truly amazing to see such an interest in Mars across the entire world, and that we're really on the verge of a totally renewed era of Martian science, with all of these missions reaching the red planet next year.
Video may have killed the radio star, but there are still a few folks out there like me who love and respect the wondrous workings of radio astronomy, so the radio star is still out there. But even I shy away from the black boxiest of all radio observations, which is a little thing called polarimetry. Not even going to try to explain it. I'm really making myself look stupid tonight, but electromagnetism is hard. So here's the basic deal. Typical radio observations treat light as a wave, right? Wave can be photon. Light can be a particle, or it can be a wave. And at long wavelengths, it's just a wave. And typically we only measure one part of the wave, which is the electric field component. And that's enough for most radio observations. But if you thirst for more knowledge, you can tune your observations to get the other polarization. You can get the perpendicular component. No, not as the B movie, but the B field. And doing this allows you to measure both the direction and the strength of magnetic fields inside galaxies. But unfortunately, the data ends up being a complicated mess of just tiny arrows most of the time. And is far less satisfying than, say, a resolved black hole image. But a team of very good data visualizers, their data viz team, is amazing. And we got this really cool thing. And this was led by Dr. Yelena Stein from Strasbourg, France, who found a way to make polarimetry exciting as a member of a project called Continuum Halos in Nearby Galaxies, which uses the Very Large Array, again, in the vast wastelands of New Mexico, to look at galaxies at radio wavelengths. And out of their sample of 35 galaxies, one stood out. NGC 4217 is located 67, I can read numbers, 67 million light years from Earth, near the constellation of Ursa Major. And the optical component of the edge-on image that you're looking at, so the purple kind of edge-on disk, is actually taken from the what? Sloan Digital Sky Survey, because time is a circle. And also the Kitt Peak National Observatory in Arizona also contributed some of the specks that you're seeing in the visible. But the structure of the magnetic fields, which are the wispy things that you're seeing coming out of the galaxy, it's enveloping the galaxy in a really thick halo, which is truly mesmerizing. They're detected at a vertical extent of 22,500 light years away from the main disk of the galaxy, which is the furthest extent of a magnetic field, an extragalactic magnetic field that we've ever measured. And instead of just a simple like circular halo, you can see multiple structures coming out here. You see an X structure and two large bubbles that are creatively called super bubbles, and even what they call a double helix structure. I think it's a little bit of a stretch. You kind of have to like close one eye to see it, but they call it a double helix, just like the DNA that makes us, because I guess the universe got bored making new shapes. But astronomers are perplexed when it comes to the origin of these mysterious B fields. It's likely due to the movement of plasma within the galaxy. And we know vaguely that magnetic fields are important in processes like star formation, but the star formation simulators know more about magnetic fields than I do. And usually we ignore B fields because they're hard to observe and it's hard to do the math. So it's just like, you know, that's one of those things that maybe I don't need to know more about. But some theories propose that magnetic fields are generated in the fierce stellar winds that result from massive supernova explosions, which could explain the very large array of structures that we see within a single B field. So these results are soon to be published in the journal Astronomy and Astrophysics, and hopefully we'll have some more answers soon, but like many things in the universe, lots of things will remain a mystery for years to come. But I think that this image is just like a really beautiful representation of radio astronomy and the power that it holds, the international implications that that has, and I just think this is really cool. So I hope you do too.
I really did not even know that radio could do magnetic fields. So
it really can. Yeah.
It really does make sense that it can, but I never thought about it.
It's a very fringe field. There's like 2 people in the world that can do it.
I mean, again, you know, as astronomers will say, oh, well, you know, it could be magnetic fields. So
yep. It's just a thing we like to blame for our problems.
Great.
Thanks for listening, everybody.
Hope you enjoyed the news. Oh, let me.
Thank you. I got you. I got it.
Thank you. I remembered how to set it up.
You did a great job with the
Halfway
whole
there. The one brain cell. You said two brain. If I had the two brain cells, then it would have been okay.
two requires for closing, and it's fine. We don't need that. You guys were amazing. Thank you. Yes, magnetic fields are just black magic, and we don't understand them, but I'm glad that we can see them in the radio, and radio is super powerful. Whatever. All right. Thank you. Thank you again.
You just delete us.
Oh my God. For anyone new to the show, I don't understand the yeet thing, so I'm too old for that. All right, so on that note, next up we have our final speaker. So KeShawn, if you can join me here. KeShawn is going to be telling us about improving the methods of galactic archaeology. Before he was at Fisk Vanderbilt, he got a BA in astronomy and French studies from Rice University. During that time, he joined the American Astronomical Society Site Visit Oversight Committee, which I'm sure has a great acronym, helping to establish protocol for astronomy departments nationwide to request site visits, which assess their climate and inclusivity. He also served in the search committee for the Association of Universities for Research and Astronomy's chief diversity officer. Now, outside of class, he travels around Nashville, bringing the stars to local students with his traveling planetarium. And beyond space, he loves to write and always loves singing and arranging, sometimes even composing music. Thank you for being here, KeShawn. Go ahead and take it away.
Hello, everybody. Let me just share my screen real fast. Okay. Everybody can see everything.
Perfect.
Okay, awesome. Hello again. So my name is KeShawn Ivory. I am a rising second year grad student at the Fisk Vanderbilt Bridge program in Nashville, Tennessee. And tonight, Dakotah and Chima talked about exoplanets. And so for my talk, I'm going to ask everybody to kind of zoom out a bit in their minds, and we're going to talk about the entire galaxy. So we're going to talk about improving methods of galactic archaeology. This work was advised by Professor Charlie Conroy and Dr. Phil Cargile at the Harvard-Smithsonian Center for Astrophysics, where Chima works. And this is research I did a few years ago in 2017, my last big project before I kind of focused on finishing undergrad, did some equity and inclusion work, started grad school, and now hit me up in a few months and hopefully I'll have a talk ready about my current stuff. So let's get started. I assume you probably wonder what galactic archaeology is. So to kind of help you out with that, here is a picture of Chichen Itza in the Yucatan in Mexico. And if you think about archaeology as a social science, it's basically using artifacts to study human history and try to establish a chronology for the history of a place or an era. And so as a kind of a visual metaphor to explain that, projected onto Chichen Itza is like this modern light projection. So it's this idea that we use modern tools and techniques to study sometimes very ancient histories. And so the astrophysical sort of analog to that is using our modern astro techniques to study the history of the Milky Way and figure out basically how it got here, why it looks the way it does, why it's structured that way, et cetera. And so obviously this is not the Milky Way because we're in it, so you can't really take a picture, can't zoom out like that. But this is essentially what it looks like. It's a spiral galaxy and it's got similar structure. And I'll be referring back to that structure as I progress in the talk. So if this is galactic archaeology, what are the actual artifacts? What are the things that we're looking for and how do we do that? So Professor Charlie Conroy, my advisor for this project, had this survey that he called the H3 survey. And the 3 H's are stellar halo at high resolution with hectoshell. So one at a time, stellar halo. So looking back at this spiral galaxy structure, the arms, the spiral part, that's all in the disk. That's like a plane. It's a very flat, thin part of the galaxy. And in the center is the fuzzy part there. We call that the bulge. And the halo, you can't see it kind of all in one go because it's sort of everything else. It's the big spherical region that kind of surrounds the whole thing. It's everything above the disk. It's everything below the disk. It's just the everything else region. And so Professor Conroy is interested in figuring out how the halo was assembled, why it looks the way it does, what the different stellar populations look like within the halo. So that's the first H. High resolution means exactly what you think it means, like your TV, right? We can see a lot of fine detail in the data, and I'll talk about what those data inputs are in a second. Hexashell is just the name of an instrument. It's just the name of the spectrograph that was used for this survey. And when I was doing this work, the survey had yet to happen. It was going to happen in the fall, and this was during the summer. But now it's 3 years later, so the survey has been running for a while. So what are the actual artifacts? What are we looking at? We're looking for when we look at these stars. We're looking for parameters, which are just like properties of stars, such as I've outlined a few. Effective temperature, that's how hot the star is. Rotational velocity, just how fast it's spinning. Metallicity, that's the presence of elements that are heavier than helium. In astronomy, we just kind of call everything heavier than helium a metal. Chemists hate that, but we do it. It's useful. And then surface gravity, which is gravity at the surface of the star, right? Self-explanatory. And then radial velocity I've got highlighted because it's particularly important. And Chima brought up radial velocity earlier in the context of an exoplanet. So he talked about that wobble that a star will do in response to the gravity from the planet that's orbiting it. But generally, more broadly, it just kind of refers to the velocity along your line of sight, like line of sight motion. So to help you understand why that matters or why we'd be interested in that, I have a diagram there for you. So the gray entity that's labeled Earth is Earth. We are there for better or worse. We're there, don't know for how long, but we're there. The yellow thing is a star. Pick your favorite one, but it needs to be kind of far away. So maybe not like the sun or something, but farther away. So I have a grid, an XYZ coordinates. So X and Y form what's called proper motion. And that's just motion that is measurable using position. So if you look out in the night sky, say the star is there, take down its position, measure it again some time later, it's over there, take its position. If it moved in between, we can calculate how much that was just by using position. That Z coordinate is the radial velocity. So it's the line of sight motion that you wouldn't be able to measure just by position, because if it's already a tiny dot in the sky and it gets further away, you're not really gonna see it get smaller. So for that, we have to use light. And I'll talk about that in a second. But that's particularly important information because it's more difficult to measure, but if you can get it, then you have all 3 dimensions of motion and you can get a really clear picture of what stars might have formed out of the same group or in the same place, and you can get a sense of how the halo was assembled, which is kind of the point of this whole thing. So now what are the actual data inputs, right? Like how do you look at light and get information out? So maybe you've seen this before. This is the spectrum. On one axis, you've got wavelengths or colors of light. And on the other axis, you have the intensity of light in that color. And you can see all these dips that correspond to, in this case, different hydrogen transitions, hydrogen alpha, beta, gamma. Basically, every jump that an electron makes in an atom has its own little signature that you can pick out of a spectrum to tell which elements are present. But that's not all. There's more, folks. You can also tell things from the width of a line, the depth of the line, how broad the profile of the line is. So much information can be teased out of a spectrum. The problem being, it's kind of expensive. You got to keep that telescope trained on one object for a long time because you have to collect a lot of light to get this much detail, right? So what if there was a way to get maybe not quite as much detail, but still good information, but faster and cheaper and easier? What if you could just take light in filters and kind of like bin it, right? So this is a thing, we do it all the time. It's called photometry. So you can see the filters are ultraviolet, blue, visible, which is kind of like greeny-ish, red, and then beyond that there is an infrared, but you can't really see it on this plot. But essentially we just take light between a range of wavelengths, bin it into a filter, and it's so much faster. You do lose some info in the process, but it's still beneficial for many purposes. And so the analogy I like to make is that if the spectrum is like going to the doctor and getting your full checkup with all the information, photometry, or the spectral energy distribution, SED, which is what I'll call it from now on, is more like getting your vitals taken. So you do lose some info, but it's so much cheaper. And if something's really the matter or that big of a deal, you'll know. So the actual code that we used that summer, I'm gonna talk about that for a while. It was called the pane. named after Cecilia Payne-Gaposchkin, a famous Harvard astrophysicist who used spectra in her work. And so I have the most vivid memory of sitting next to Dr. Phil Cargile, a postdoc. He was from Fort Worth, I'm from Dallas, so we had that in common. And we sat down and he basically just unloaded this whole code, this whole process on me. And so now it is your turn to get schooled on how this code works. So essentially, the code fits both SEDs, which is the cheaper, easier, the vitals, right? The photometry where you filter it into bins, and the spectra, which is the full checkup, the whole expensive process. This fits both of those things to get those artifacts, those properties, those parameters, temperature, metallicity, things like that. So the way it actually does that is by a combination of models and deep learning. So this grid of models was made by Professor Charlie Conroy, the advisor for this project, called C3K. And basically what it is, it's a collection of SED and spectra along with the properties, temperature, metallicity, things like that. And the code trains on that grid and it learns to recognize patterns between what a spectrum looks like, what an SED looks like, and then what all those parameters are. And eventually it learns pattern recognition in a way that it can interpolate in between these different combinations, and that's deep learning. So in the end, what you can do is you can literally feed it a brand new spectrum or SED that it's never seen, and using what it's been trained on, what it knows, it can say, oh, you know what? This looks somewhere in between this spectrum that I've seen and this one that I've seen, or this SED and that SED. So I'm gonna guess the temperature is probably somewhere around here. And you can get a whole probability distribution for all these different properties that you wanna know. And so the question that emerged from this research sort of over the course of the summer was, what do we gain from fitting both things, the SED and the spectrum? What do we actually gain from using all the information available at our disposal? So the last thing I have to talk you through before I answer that question is the stats that kind of make the whole thing work. So a little bit of a stats lesson, don't worry, it'll be painless, it'll be quick. So we use a thing called Ensemble Markov Chain Monte Carlo. And despite the long name, I assure you it is extremely exciting, okay? So one by one, we'll just go through what each of these things means. Ensemble, a whole bunch, a collection. So the point of this method is you're trying to explore the entire parameter space, every combination of those properties that you could possibly think of, temperature, metallicity, those things. You want to know the probability of every combination of those things. And so this process goes a whole lot faster if you've got a lot of individual walkers, those are the entities that sample the space, individual walkers walking around instead of just one. So we used an ensemble of like 300 to sample the whole space. Markov chain is kind of the core of how this thing works. And that means forgetfully ambling about. So the way that it actually moves through the space is one individual walker is in a place and it evaluates the likelihood of somewhere else. And it says, if that likelihood is greater, I'm gonna go over there. And if it's not, I'll stay put and keep looking. The thing is, once it makes a move, it forgets everything about its past, where it came from. So it could end up going to the same spot multiple times. And sometimes they even get stuck in one spot and it's hard to get out. But this is the best way to ensure that we really do make our way around the whole space. And so I like to think that it's a really terrible way to live, but a really great way to sample when you don't think about where you came from, but just where you're going. And finally, Monte Carlo sounds like gambling, right? So it just means randomness. So there's some element of randomness that's inserted into the walk of the walker. For example, like the step size that it takes varies every time it takes a step. That's randomness. So something random is inserted. All right, so that's how we sample the whole space. Now, this looks like a lot. It's not. We're gonna step through it pretty quickly. I just want to get you ready because I'm gonna show you some plots and I want you to know what you're looking at and what to focus on. So I'm gonna show you something called corner plots, which are just a way to visualize the probability distribution resulting from sampling that whole space like we just talked about with the MCMC. And so signal to noise is a really important number. It just means the higher that value, the cleaner the data is, the more signal, the less noise. Conversely, the lower it is, the noisier the data is. And I varied, you're gonna see that I varied the amount of noise that I added to the data to see how successfully my code could recover the truths that I put in. And so the parameters that I chose for truths were temperature, how hot the star is, and metallicity, elements heavier than helium. And so those input truths, again, mock data that I put in, I added some noise to see how successfully I could get it back. Those truths were solar truths, so the values for our sun. So temperature, 5770 Kelvin, metallicity, 0 dex. Those are just solar values that I put in, added some noise, and I want to see if I can get it back. And I want to see if adding the SED and the spectrum together helps me to get it back. So the last thing is a contour plot. You are going to see essentially a contour, and it's going to be, you're going to see a contour that's essentially going to be crosshairs, and at the intersection with the crosshairs is my truths. So the temperature I put in, the metallicity I put in, those are the actual values. The size of the contour lets you know how precise the data is, and whether or not the intersection is in the contour lets you know if we're accurate. And so lastly, the two kinds of contours are, I'm gonna plot a blue one, which is just the spectrum. So that's the full checkup only. And then the red one, which is the spectral energy distribution and the spectrum. So all of the information we have available at the same time. And we're gonna see if there's a difference. There will be a difference. All right, so this is signal to noise of 100. This is the highest signal to noise that I plotted. It's the cleanest data. And this is the blue one. So it's spectrum only. And again, the contour plot on the bottom left. So the crosshairs, that's the truth. It's in the contour, so it's accurate. And it's not an enormous contour. It's precise, I guess. Adding in the SED, you'll see there's not much of a difference. Well, that's just because with data this clean, the spectrum dominates, and so you're not really going to see a difference. The SED doesn't add anything or take it away as far as accuracy or precision. So to really see the effect, you're going to have to go to noisier data. So the next value I plotted is 38. So the bottom left contour plot, in the crosshairs, it's well within the contour, so it's nice and accurate, but it's a really big contour, so it's not the most precise. So we can see if adding in the SED will change that at all, and not really. Still too clean to really notice a difference. Accuracy about the same, precision about the same. Signal is being dominated by the spectrum. If we go to a much noisier data set, so this is 5, now you can see it's not super accurate because the intersection of the crosshairs, that's the truth, it lies outside of the contour. And as far as precision, it's kind of a big contour, so it's not great either. Now, here, if we incorporate the SED, you can see the contour size snaps down a lot. So it's way more precise in terms of reducing the size of the uncertainties. And it's even more accurate because the intersection of the crosshairs is now in the contour where it was outside. So in this case, for this very noisy data, incorporating all the information we had available was quite beneficial. And so we can see the effect gets even more exacerbated at the noisiest signal to noise that I plotted. And this is important because this is around the signal to noise that the actual H3 data would be, is now, signal to noise 2. So huge contour, not super precise, but it is very accurate. The intersection is right in the middle. But if we incorporate the SED, enormous difference in terms of precision. It snaps into size, it snaps down to a much smaller size, but it's like dead on accurate. It's right in the middle. The only thing is you can see that sort of secondary peak. Not sure if one of my walkers kind of got stuck. I mentioned that can happen, but the focus here is that the truth is really dead on in the center of the contour, and the contour is a lot smaller. So incorporating all the info we had available really did help us in terms of precision and accuracy. So again, just to recap, incorporating all the information, the SED and the spectrum, increases both accuracy and precision, but especially precision of our measurements of these stellar properties or parameters. Accuracy is closer to those truths, and precision is more trustworthy results from smaller contours, smaller uncertainties. And the very last thing is just briefly, this is what I do now. Again, hopefully in a few months, I'll have a talk all about this. But right now, my work is advised by Professor Andreas Berlind at Vanderbilt. And if you zoom out one more time, galaxies organize themselves into clusters. And so just as the stellar halo surrounds one galaxy, a big halo of dark matter, which is matter that we can't actually see, but we know that it's there because of things like gravity, that surrounds the whole cluster. So right now, I'm working on a code that grabs that central galaxy, the main galaxy in the cluster, uses its mass to determine a mass for the whole dark matter halo, because we do know those things are related. And then it grabs those satellite galaxies that are gravitationally bound to the central and uses their velocities to basically like assign which satellites belong to which centrals. So I kind of just started, but hit me up in a few months. Hopefully I'll have a talk all about that. So that's it. And any questions I would be glad to take.
Awesome. Thank you, KeShawn. That was a really great talk. Also the clearest explanation of MCMC that I've ever seen in my entire life. That was awesome.
Thank you.
We do have some questions for you. So I'm going to take the prerogative to reorder some of the questions. One of them is you mentioned, and I'm mentioning it now because you're ending with this dark matter halo mention. Most of your talk, or one part of your talk, was talking about the stellar halo, and now you've mentioned the dark matter halo. What is the difference between them, or the relationship between the stellar and dark matter halos?
Right. Okay, it's a really good question. So the stellar halo, in terms of the 2017 work that most of this talk was about, we're essentially talking about the stars, like the normal matter, the stuff that electrons and protons and normal stuff that we interact with kind of on the daily. We're talking about that stuff. So that's how we're able to measure things like the temperature of those stars or the rotational velocity of those stars, because we're interested in the stars in that part of the galaxy. So stellar halo in that sense is more referring to a structural portion of a spiral galaxy. Just as you have the arms in the disk, you have the fuzzy bulge in the middle. I can actually go back to it really quickly. All right, so the arms all in the disk, again, the fuzzy bulge in the middle, and the halo kind of being everything else. It's just a structural component. The dark matter halo, there is a dark matter halo around, for example, this galaxy. It does have its own dark matter sort of envelope around it. It does, indeed. That's matter that we can't see. So unlike the stars and stuff, we can't see that, but we know that it's there because of things like gravity. And if you could zoom out even further, there's an even larger dark matter halo. So say this galaxy has smaller satellite galaxies that are bound to it gravitationally. Those would each have their own little subhalos, and there's a dark matter halo kind of around the whole thing as well. And so the big difference between the dark matter halo and the stellar halo is one is visible, one is not, and one is about the structure of a galaxy, one is sort of about this larger scale structure.
Nice, excellent. Okay, let's see. Rajesh wants to know what in the blue checkup in your code, what in the blue checkup would make you want to do a red checkup?
Right, that's a good question. So this is, the idea is that H3 is running and it's getting both of these things. It's getting both like the spectrum, and then it's also doing the bending thing and getting the photometry. And so if you're getting both, I wanted to ask the question of how beneficial is it to use everything that you're given? And so if you're already doing the blue one, the full checkup, then doing the vitals, the photometry is, I mean, you might as well, because it's like, you're already doing the hard thing, so why not do the easy thing? But now that you have both things, I want to know, is it really that helpful? And again, in the regime, going back to plots, in the regime with really clean data, it wasn't all that helpful. Not a big difference. Without SED, just the spectrum with both, right? But then you go to much noisier data too, which is around the actual data set. And you can see the precision, in particular, the precision had a really big increase when you incorporate everything at your disposal. So to answer the question very directly, if you're doing the hard thing, you might as well do the easy thing. And then once you have both, this shows you that it's good to use it all.
Nice. Have you ever, like I'm very excited by how much better it gets when you include the SED, when you do the red checkup. Have you looked at what happens if you only do the red, like you don't have the blue information, the spectra?
That's something that when I left for the summer, that's kind of where Phil wanted to kind of explore next. And that's a really good question because you would think you lose the spectrum, you're losing the hard thing, the really detailed thing. So I guess the question then would become not how much are you improving, but it'd be how much are you losing? Like, can you still get something somewhat reliable even without the spectrum? And that's where Phil wanted to kind of go next. And this is a good reminder, I should probably ask for updates on that question, but also where the survey is kind of in general, like 3 years on. But yes, that's a really good question that we were kind of thinking about playing with.
Nice, okay, excellent. We've got one more question from Pete. If galactic archaeology helps us understand how the universe evolved from helium and hydrogen to the many elements we now recognize, what can Milky Way chemistry teach us about the future of our universe?
That's really interesting. That's really interesting. So galactic archaeology, I do kind of want to clarify, it's sort of hyper-focused on, it tends to be kind of hyper-focused on the development of our own Milky Way. Really because that's the one that we can study the best, because the stars are obviously the closest to us. It's kind of the only galaxy that we have such detailed access to, with the idea being if you can understand these formation processes for like our spiral galaxy, then you understand a little bit more about generally how it works. So it's a little bit less about like that universal scale of evolution, but a lot more about our very kind of local, our galaxy scale. But to the question of what Milky Way chemistry can teach us about kind of where we're going, chemistry of these stellar regions can also be used in kind of the same way as some of these other properties that I've been talking about, because you want to know which stars might have formed in the same regions out of the same groups. So you can use the sort of the kinematics, which is what I was saying about positions and also velocities, to figure that out. But you can also look at chemistry, because they've got similar chemistry. You can kind of conclude maybe they come from the same place. And so using Milky Way chemistry, you can get a sense of which things are kind of linked, and you know kind of what to watch and what to look out for. And as you kind of watch it in real time, you can kind of see the process play out. I don't know how much you could actually glean about what's next, because the formation is still, we don't know much about it, right? But you could definitely watch it play out and learn a bit just from the chemistry about the structure.
Very, very cool. That's also fascinating to me. I study galaxies in the very distant universe. So my galaxies are like a couple of pixels, and it's mind-blowing how much power you have to learn about what's going on in our own galaxy. That's really cool.
Right. Exactly.
Thank you again for your great talk. We look forward to hearing about your dark matter halo project. That'll be exciting. We'll look forward to that in the future. I'm going to ask Rebecca to join me, and we will ask you to join us again at the end in a few minutes, KeShawn. Thank you.
Hello.
Yeah, no problem.
Good job, KeShawn. Thank you. All right. Good show. Good job, everyone. I'm a little premature here on the slides, but so we are going to be bringing our speakers back. So if there were any questions that you had that didn't get answered, or if any of the questions that were asked sparked new ones, please go ahead and put those in the chat, and we'll bring all of our speakers back here in just a minute to answer any more of your questions. But if you want trivia answers, we will give those to you later this week. So stay tuned. We will put them on our website. So go ahead, check out the new website at aotatx.org/trivia if you want to find those answers. And again, you don't have to get them all right to win a prize. Please just let us know that you were here, that you were interested, and connect with us on any of those social media apps.
And if you are watching this show as a recording, we will keep the trivia open until Friday or the end of the day on Friday. So you still can play trivia even if you're watching the show later in the week.
Yes. Again, a big thanks to the North Door. So our venue that we are normally physically located at, shout out to them for being such great hosts. And we hope that soon it will be safe to be back there.
A huge thank you to tonight's awesome speakers, and also to all of the Space Cadets and the AoTATX committee members who are behind the scenes, running the questions, helping in the chat, giving you useful links. This is a big group of people who are putting this show together. It's not just me and Rebecca who you see, it's a whole bunch of awesome people behind the scenes. So thank you to everybody.
Yes, specific shout outs to Sam and to Drea for being our chat admins, and to Logan, who is here from Space Drafts in Tucson, helping us out as well. But mostly a big thank you to you, the audience. We wouldn't have this show if it weren't for you showing up every month for the past 5 and change years. We really appreciate the opportunity to keep bringing you astronomy and really interesting science. So if you are enjoying the show, please reach out, let us know if there's anything that you would like to see.
As Rebecca said, our show would not be possible in normal times without our awesome venue, the North Door. Please consider supporting the bartenders, everyone who works there. Maybe what you would have spent on a beer or a tip or something if we were at the show in real space. And also, don't forget that you can still get Pueblo Viejo tacos every day, which is what I will be doing from now on.
Every single day.
Every single day.
All of the tacos. All right, our next show will be August 18th, which is a Tuesday night, the third Tuesday of the month. We are back to our regular schedule at 7:30 p.m. Central. It will also still be virtual, so join us in your living room or wherever you're tuning in from. We have Jacqueline in India telling us stories of the African sky and talking about space medicine, and we will have even more for you. So stay tuned, follow us on social media, sign up for our newsletter so you can find out more information about that.
Go.
No, I was gonna say, and again with the follow.
Again, you can find us on all the things. You can find us on YouTube, watch some of our older videos from other talks on Facebook, Twitter, Instagram, reach out to us by email, or check out our website, AoTATX.org. And I don't know if Rebecca mentioned it, I think we still have our survey open. And so if we can throw that in the links, but we have a survey that you can answer a couple of questions to tell us what kinds of things you'd like to see more of in the show. And maybe you can add to that what kinds of things you'd like to see on our website. So it's an in-progress website, but there's a lot of information there, and check it out.
Yes, so the link to the survey is in the YouTube description, and our wonderful Space Cadets are putting that in the chat for you. So that is all we have for our regularly scheduled show tonight. But if we could please bring back all of our speakers so we can finish answering some leftover questions. Perfect. Awesome. Okay, so we have a question from the news segments. So I just wanted to give Jackie a chance to explain some more about magnetic fields. So we had a question about how many parsecs is it to those magnetic fields, or how many parsecs is it across? I'm not quite sure what the actual question is, but what's the scale of those magnetic fields according to the galaxy?
Yeah, I'm assuming that question came from the fact that I said that the width was 22,000 light years. So a light year is how far a beam of light travels in 1 year, but a parsec is a more reasonable unit of distance that we tend to use. It's a parallel arc second, whatever. Anyway, it's like a factor of 4. So I did the math, and that's about 7,000 parsecs or 7 kiloparsecs. And for reference, the Milky Way disk is about 8 kiloparsecs from end to end. So the vertical height of these magnetic fields is the width of the entire Milky Way galaxy. So basically, it's blowing out as much ionized plasma in height as it is in width. So that's pretty cool.
Pretty freaking big.
Yeah.
Yeah.
I have a question for Dakotah. So I guess on your exoplanet talk, when you were showing the methods that exoplanets are detected with, a question is, what are timing variations and orbital brightness modulation, and will JWST be able to do either of those?
So and by the way, there's a resource, there's a link that has a paper that talks about all of the different variations or all the different methods to detect exoplanets. The question was, what are timing variations, right? Timing
variations and orbital brightness modulation.
Right. So there some, I don't know. I actually don't know what orbital brightness modulations are. It's in that paper though. But I think timing variations have more to do with, it's another way to infer that you have a planet. You have like some sort of periodicity that is being that we're recording due to the fact that there is a planet that's there. I'm pretty sure that the first exoplanet ever recorded was observed in some sort of timing variation. It was around a pulsar, which is an unusual star to find a planet, especially for the first time. So yeah, I don't know about the orbital modulation. That's not in my area of expertise. But I do know that by far the two easiest ways of finding these exoplanets are radial velocity and the exoplanet transits, which is why the plot is dominated with those. Sometimes there's these niche ways of looking them up. I know microlensing is another one where it's like if you just randomly get very lucky, you can look in the right place and gravity will have warped the space in such a way that you can see a planet behind a star. And I think that's actually how the other Uranus-sized planet that we found was, or the only other one that we found was. But yeah, check out those resources, because there's really like 10 or 15 different ways, and I'm not familiar with all of them.
Nice, excellent. Yeah, we just posted that link again that you mentioned with the resources. Thanks.
I have a question I think I'm going to open up to everyone. We had a question about if the astronomy community had the same budget as the Department of Defense, what kind of observatory would you like to see funded?
Interferometer on the moon.
No hesitation. Absolutely. Put some dishes on the moon. Got it. Great. Like a big, like how big? Bigger than what we have on Earth?
I want like an ALMA on the moon so that you get the baselines on the moon, but then you also hook it up to the ALMA on the Earth so you get the baseline from moon to Earth.
So
it's a great idea.
Bigger than the Event Horizon telescope that was
correct.
The entire size of the Earth. Okay, all right. Yeah. So we just want to one-up the black hole people.
Yes.
Yeah, all right, I got it. Cool. Anyone else?
Honestly, if you had the funding that the military had, you could do that and so much more. But I would keep it simple. I just want the two concept missions, Habex and Luvar, both to be done. I'd be very happy with that.
Yes, yes. It would be great if all of the things that we already are asking for would get funded, because they all have really great uses and purposes. And it's not just space-based telescopes too. I mean, there's some really big ground-based ones that are in the works and being planned, and I think were mentioned earlier in some talks, but also would be really helpful to kind of fill in some of the gaps in our technological capabilities right now.
Yeah, if we were getting that funding every year, I would say go to the moon and build an entire society that is purely dedicated to studying various things in astronomy. Like every year, if we get that every year, yeah, just do whatever, go crazy.
I mean, yeah, do whatever, because like I've never I've never thought about this exact question worded this way, only because it would take a massive restructuring of the American ethos for this kind of thing to ever actually happen. But should this actually happen, I don't know. I guess keeping in line with the question that was asked about galactic archaeology, maybe a telescope that could, the same kind of questions we're asking about the stars in this galaxy, a telescope that could handle those same kind of questions for others, so that while we're uncovering kind of the formation history of ours, we could do at a similar, well, it'll never be like the same quality, but like a much greater quality, like other galaxies too, I guess. So like expanding the practice of galactic archaeology in scale might be interesting.
Putting our own galaxy into context in the universe. Yeah, that would be great. I, as a person who studies other galaxies, I would love to have more detail than two pixels, like Kayla mentioned earlier. We had a comment about your signal to noise of 2, KeShawn, and I'll let you know that is the same in the high, most distant galaxy universe. I would be very happy if I found a signal to noise of 2 emission line. I feel your pain coming from a completely different location.
Yep, exactly.
Yeah. Michaela, I think we have one more question. A lot of screens to look at. I'm sorry. There's like a lot.
I have a question for KeShawn about MCMC. What types of problems is it like well suited to solve, and what are there problems in astronomy that are not well suited for MCMC?
Sure. In terms of problems that it's not well suited to solve, this question answers itself pretty well, actually, because in terms of problems that MCMC is not really needed for, my current work, I don't do anything with MCMC in my current work because there's really no need. All I do now is, okay, so you have a bunch of galaxies in the table, you know their masses. I want to take the biggest one that you've got, look at its mass, use an equation, like literally an equation from a paper and the uncertainty associated with it, assign a mass for the halo the whole dark matter halo that galaxy lives in, and then use velocities to assign it satellites. All of that is like a big stats problem. It's just a bunch of probability. There's really, MCMC would complicate that needlessly, you know? And there is a paper out that I'm actually supposed to be reading like today about using machine learning for like assembling galaxy samples. But even that is like a slightly different thing because mine is like once you have the sample, you want to make a group, right? MCMC is really good for the pains purposes because we have an enormous like parameter space. We had like something, I want to say like 19 different parameters from like temperature, metallicity, velocities, and all the way down to observational things like the blaze function, which is the instrument you're using has an impact on like the data you get from it, and you want to be able to subtract that as well. So altogether like 19 different kinds of parameters to fit for. And so a space like that, MCMC is great because you use 300 walkers to walk around the whole space. You make sure that you get everywhere because of the methodology we talked about. And so it's good for those really complex problems.
Cool, awesome, thank you.
All right, I think that is all of the questions that we have today. So I just wanted to give another special thank you to all of our speakers for being here. You're all doing really amazing science, and I'm really grateful that you could share it with us and with our audience. We have links to their websites and their social media. Please go check them out, follow them, see what they're working on. They are all going to be in the chat and in the YouTube description, so you can get to those easily. We also have some links as references for some of the things that were discussed in the talk. If there's something you want to learn more about, please go ahead and check those out. We also encourage you to follow Jackie and Danny because they're amazing and hilarious humans. And I just want to say good job. Thanks for doing a great show tonight, guys.
Thank you.
Thank you, everyone.
Have a great night.
Bye, everybody.
Bye.